All right, now we're going to start something completely different. We're looking at what it says normal distribution. What does that mean when something is normal distribution? It has a bell curve. If it's normal, it means it could be represented by a bell curve. Remember what the middle of the bell curve is? What value goes there? The mean. If you're doing a sample, then it's X bar. If you're doing a population, then it's the mu. And then we have three standard deviations to both sides. We've looked at these, we talked about them before. We specifically talk about distributions at the positive and negative two standard deviations. What do we use that for? What did we use that for? For significance. If it's beyond the negative two standard deviations, it's significantly low. If it's above two standard deviations to the right, it's significantly high. If it's in between those, it's not really that significant. In other words, not much will change from out of what we expect is going to happen. And we'll talk about more of these in chapter 8 when we do hypothesis testing. All right. Last time we discussed discrete probabilities. What do we mean by discrete probabilities? This is in chapter 5. Thank you. When we say discrete probabilities, what are we talking about? What's a discrete number? Yeah, integers, whole numbers. So it's something that could be very easily gotten to. Now we're going to look at continuous probabilities. When we talk about discrete, whole numbers that are finite, and continuous are decimals that can't be infinite. It sounds like a redundant statement. Decimals that can be infinite. Because the second you start talking about decimals, you talk about infinity. For example, how many numbers are there between 0 and 1? Bless you. There's an infinite number of numbers between 0 and 1. Actually, there's an infinite number of numbers between 0.01 and 0.02. There's an infinite number between there. So now when we talk about continuity is continuous functions or probabilities. We're looking at now, it could be any value we want to. All right, here's a chapter problem. So you want to fly a U.S. Air Force jet. Do you satisfy the U.S. Air Force requirements having the height between 64 and 77 inches? You don't have the sheets yet, so you don't look for them. You don't have anything yet. You must be between 64 inches and 77 inches tall. Why do you think that is?
If you too short, you might not be able to reach that.
The pedals?
Or if you're too tall, you might hit the top.
Exactly. That's called ergonomics. It's the design, the study of tools, equipment, and the management of those so that it's a safe environment, so it can be used safely and repeatedly. How many times have you been in the car and you drove by somebody and they could barely look over the dashboard? And yet they're going down the highway at 80 miles an hour and they can't see where they're going. But in military, there's more than just the height. It also has to do with your width. Because here we say weight, because there are people who are heavy who are thin but muscular, as opposed to just round. Because you have to fit in the cockpit. And so you have to be able to reach and touch all the instruments that are all the way around you. Here's some more. The U.S. Air Force requires that its pilots must have a height between 64 and 77 inches in height. The U.S. Army requires that women must be between 58 and 80 inches tall. Same reason there, because they have all these equipments that are already designed for people that height. You have the flak jackets, so the metal, the bulletproof jackets. You have the uniforms. So they don't have to go out and buy a whole bunch of new stuff, people who are too short or way too tall. Section 4.4.2 of the U.S. Disabilities Act relates to height clearances of entryways. It says walks, halls, corridors, passageways, aisles, and other circulation spaces should have 80 inches minimum clear headroom. 80 inches of clear headroom. How tall is 80 inches? It's 6 feet 8 inches. That's pretty tall. The reason I say that is because not many people are higher than 6 feet 8 inches tall. And if you had a basketball team, yes, you might have a whole bunch of them. But so they're saying on the average, this is what it should look like. Also, the width of doors, they have to be a certain width so people with wheelchairs can go through. If they're not, if somebody builds a building that doesn't satisfy those, guess what they have to do? Tear it down and try it again. Stairs are the same thing. Stairs have to have a certain height to distance ratio. And if they're not, then they have to be torn down and done again. The elevators at the San Francisco Airport car rental facility has a placard indicating the maximum load of 4,000 pounds or 27 passengers. Which one of those two you think is more important? 4,000 pounds. Why? Well, what if you have a bunch of, we have 40 little kids? How much are they gonna weigh? At most 50 pounds each, yeah, 60 pounds. I was watching this one show called Air Disasters, where the weight balance dynamics of an airplane there's a certain envelope that the weight of the passengers and luggage and fuel cannot exceed so the airplane can take off. The pilot did the calculations. They were well within the parameters, but they crashed anyway. They couldn't take off. Why? Well, think about when these rules were made back 40, 50 years ago, were people as heavy as we are today? No, we're pretty much lazy. We're nothing but, I'm surprised the earth doesn't wobble because of our weight in America. We're just a fat nation. So when they say 27 people, I mean, you're looking at 200 pounds a person on the average. Now, airplanes, can they ask the passengers, tell me how heavy you are so you see exactly how much weight we have? They know how much the luggage weighs. They weighed it already. Now, to have a perfect example of how much weight they have on the airplane, they'd have to know what everybody else's weight are. Would you feel comfortable standing on a scale at the airport? To me, I couldn't care less. I mean, if you're fat, you're fat. I mean, there's no way you can hide it. And I always made a joke. You have Gamblers Anonymous, Alcohol Anonymous, Smoker. How can you have an Overeaters Anonymous? How anonymous can you be when you're 300 pounds? Yes, you overeat. You see it. So, but now the thing is, these rules that they're making nowadays have to be rewritten because we are not the same as we were 20, 30, 40, 50 years ago. A Disney requirement for someone who wants to be employed as Tinkerbell. It has to be between 58 and 62 inches tall. Because you have to be able to fit in those uniforms. Radio City Music Hall, the Rockette dancers must be female and heights between 66 and 70.5 inches tall. Why? Exactly. So when they get in line to do the high kicks, they're a perfect line. Because you're looking at 66 to 70 inches, you're looking at less than 7 inches, 6.5 inches difference. That's this much. And they have them deviated around so it looks good. The Bombardier Dash 8 aircraft carries 37 passengers, and fuel and baggage allotments total of 6,200 pounds. So think about it. It weighs 1 gallon of fuel weighs 6 pounds. And airplanes carry a couple of 100 gallons, easy, for a short flight. So now we're looking at how much luggage can you carry, how much people can you carry if your maximum weight allotment is 6,200 pounds. When women were finally allowed to become pilots of jet fighters, engineers needed to redesign the ejection seat because they were originally designed for men weighing 140 to 100 or 211 pounds. What would happen to a lady that's under 140 pounds if she ejected from an airplane? The force of the ejection seat, the force of the wind coming at you would pretty much crush her to pieces, like an aluminum can. So they had to redesign those jets to modify for those. But anyway, there's a whole bunch of more examples like that too. Oh, here's some examples of things that went wrong. Ergonomic problems often involve extremely important safety issues. Here's some real world examples. When we have an emergency from Air Midway 5480, says pilot Katie Leslie, just before her beach plane crashed into Charlotte, North Carolina, resulting in the death of all 21 crew and passengers. Excessive weight of the passengers was suspected to be the contributing factor. After 20 passengers perished in the Ethan Allen tour boat that capsized on New York Lake George, an investigation showed that although the number of passengers was below the maximum allowed, the boat should have been certified for much smaller number of passengers. Water taxi in Baltimore sank in the inner harbor, killing 5 of the 25 people on board. The boat was certified to carry 25 passengers, but the total weight exceeded the safety load of 3,500 pounds. So, if you're ever asked your weight at the airport, do not be embarrassed. It's either that or crash. All right, so back to this. Standard normal distributions. Here are the parameters. These are the properties of something that is standard normal distribution. The properties. First off, data must be bell-shaped. Standard normal distribution has a mean of 0. And the standard distribution must equal 1. Basically, what this thing is telling us what? Has to be bell-shaped, and the mean has to be 0. So what is that going to tell us if the mean is 0? If the mean is 0, what do we know about our data? Hmm? If the mean, what is the mean? The mean is the average. So the average of all of this stuff is 0, which means that both halves of this curve, of the data curve, have to be equal. The amount of data on the left side must equal the amount of data on the right-hand side. So since the mean is 0, that means we have negative numbers here and positive numbers here. What are we looking for? With standard normal distributions, what are we looking for? Why would you use something? We haven't discussed that yet. What is the whole purpose of this? We want to know the probability of a specific event occurring within the domain of the data. So basically, remember we talked about probability? I want to know what is the probability that X is greater than 2? If we're looking at one die being tossed. What's the probability that the one roll gives you a number greater than 2? So how would you find that out? What's that? Well, you only have one die being tossed. You're getting a number greater than 2. You have one die, you roll it. What's the chance of getting a bigger number than 2? Why do you say 4 out of 6? Okay, so yes. So the probability of winning would be what? 3 or 4 or 5 or a 6. And there are 6 sides on a die. So there's 6 possibilities. So what's the probability of rolling a 3? There's 1 out of 6. Or means plus, so that's 1. Getting a 4 is 1 out of 6. 1 out of 6. 1 out of 6. So the probability is 2 over 3. 2 out of 3. So basically what it's telling you is this. The interpretation of this is if I had one die and I tossed it, if I tossed it 3 times, 2 of those numbers should be bigger than 2. Is there another way we could figure that out? We want a number bigger than 2. What don't we want? X is not greater than 2. This is the negation of it, the not value. So it means the probability of getting a 1 or a 2 out of 6. So it's 1 plus 1 out of 6, 2 out of 6, which makes it 1/3. We don't want something smaller than 2, or 2 or smaller. So if we take 1 minus what we don't want, so 1 minus 1/3 is 3 over 3 minus 1 over 3 is 2/3. That gives us what we want. You don't always have to go straight to the answer. You can find another way to doing it. But this is what we call discrete probabilities. This is an example of discrete probabilities. Let's look at the height of people. Is that a discrete number or is it a continuous number? It's continuous. Yeah, because all of us in here have different heights. Actually, I bet you to find 3 people who have the exact same height in this school, you'd have to go through a couple of thousand students. Because you can go to decimals now. Somebody could be 6'1" 6'1.5" So that's what makes it a continuous probability. Now, since it's continuous, we have our mean in the middle, and we have standard deviations of both sides. How do we go about and calculate these? The formula we use to convert from our discrete numbers to our continuous numbers is something called the z-score. And we'll go more into it than there. And we're going to use this formula in a second. And the formula we use to define the bell curve and don't worry about you don't have to memorize this one because you never really use it actually. It's given to you most of the time. Remember what this represented? Standard deviation of the population. This is mu. The mean of the population. So here's another row down here. And what is E? E is called Euler's constant. E is 2.7181879. It's a constant. It's called nature's constant. So this formula defines our curve. And somehow we're going to eventually start using this formula to find a value that will help us find the probability of what we're looking for. You notice how the z-score, as it gives us a specific value, relates to the mean of the sample minus the mean of the population over standard deviation of the population. And we'll start using chart. I gave you the charts for it. And we'll start using those in a second. So basically, since we're dealing with this formula here is the area under the curve is our probability. Actually, it means a little bit more than that, because what's really cool about this, remember, whenever we talk about probability, we're talking about probability distributions. Distributions represent our data, entire population of data, and how it relates to what we have. So this is the first very important concept, is we have the area under the curve equals the probability of what we're looking for. That's muy importante. That's something else. Oh, yeah. We're talking about something called a uniform distribution. A continuous random variable has a uniform distribution if its values are equally spread over the range of possible outcomes. A continuous random variable is uniformly distributed if its values are equally distributed, which means every value has a same probability of being selected according to where it's situated in the bell curve. Let's define density curve, because this is what we're going to be dealing with from here on out. Density curve is the graph of any continuous probability distribution is called a density curve. And a property of it is the area under the curve must equal 1. Now, this is what gives area and probability a connection. Because this density curve has to have, because remember, the probabilities, the sum of all your probabilities has to equal 1, and the area under the curve, all of those together has to equal 1. So each area under a curve is equal to a probability of some sort. So let's look at example 1. It says, during certain times, at JFK Airport in New York, Passengers arriving at the security gate checkpoint have waiting times that are uniformly distributed. Between 0 and 5 minutes. How do we represent that in a graph? So you start off at 0, then you go to 1, 2, 3, 4. How far do I go? To 5. And they all have equal, they're uniformly distributed. So they all have the equal amount of time between 0 and 5 minutes. So it doesn't matter if you get to the airport 5 minutes early or 1 minute early or just when your time is to get in, your wait time is the same. Let's see what the question is going to be. So what are the waiting times? Remember, all of these areas, what do they have to equal to? Yeah, so the area of this one plus the area of this one plus the area of this one, all of those areas has to equal 1. This is the waiting time. So how much are they? How much are each of those times? 1, 2, 3, 4, 5. So we have 5 times this wherever the X is.
Have a wait time of 0.
Just when you get there. Because yeah, from 0 to 1 minute is there. From 1 minute to 2 minutes. Remember, these are discrete. And these are continuous, so it's anytime between there. So what is X? I divide both sides by 5. One divided by 5. Does 5 go into 1? No. So I put a decimal. So I put 0. Does 5 go into 10? So they each have the same allotment of time of 0.2 minutes of waiting time. This is the waiting time. So what's the question being asked here? Find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So this is your f of x, your probability of waiting, p of x, I say, probability of waiting. Very important. What is the formula for p of x? What is the formula for each of these probabilities? 1 over the range. Okay, so we have this. So the area, I mean, the time of each one is 0.02. So what was the question? Find the probability that a randomly selected passenger has a wait time greater at least 2 minutes of at least 2 minutes. So how would you do that? Remember, we're looking for the probability of the passenger waiting at least 2 minutes. So how do we do that? Actually, there's 2 ways we can do it. One of them, we can use addition. One way we can use multiplication. So when it says at least 2 minutes, what is it saying? It starts off at 2. So it goes from 2 to 3, from 3 to 4, from 4 to 5. So it can be the probability of 2 plus the probability of 3 plus the probability of 4. Because this is from 2 to 3, from 3 to 4, and from 4 to 5. What's the probability of each one of those boxes? What's the probability of each box? Is 0.2. So we have 0.2, 0.2, 0.2, which is 0.6. Your probability of selecting somebody that waited at least 2 minutes is 0.6. But remember, we just talked about this is probability. Probability is the same as what? Probability is the same as area. So we're looking at least 2. We want to know what is that area. So the area of at least 2 minutes, what's the formula for area? Of rectangles. Yeah, base times height. So the base is what? From this number to this number is how far? 1, 2, 3. How tall is it? 0.2. 0.2 times 3 is 0.6. That's the beauty of it, is now we can start using the rules of areas of algebra to start solving these things. That's a pretty easy one. That's since all of these occurred the same. But will it always happen that way? No, especially since we're dealing with standard normal distributions. Since we're looking at the bell curve now, the middle has to be 0 because the average has to be 0. So we have 1, 2, 3 to the right, -1, -2, -3 to the left. What should the area inside this bubble be? 1.0. So this is the normal standard distribution. It has 1. The mean is equal to 0. The area equals to 1. Each standard deviation equals 1. You see, so here's your mean. So 1 standard deviation, 2 standard deviations, 3. So all your standard deviations are all 1. So what we're going to start using, we're going to start looking at those charts that I gave you. Let me find an example. We'll start using those charts. Well, let me first show you how to use those charts. With the chart, these numbers inside here are the area inside that curve of the shaded region. There should be over there. So the numbers inside here is the area under the shaded region under the curve. So whatever z-score that we get, whatever z value you get, it always reads to the left. This area is what is inside this curve, this chart. All right, now if you notice, this is the z-score. It has a z on the top of the corner. On the vertical column, you have the first number on both sides of the decimal. It goes from zeros, actually, it goes to 0 on the bottom. It goes all the way up to 3, 4. And then on the horizontal bar on top, you always have a 0.01, 0.02, 0.03. So you have the second digit. It goes all the way up to 0.9 or 0.09. So, for example, if we had a number we had a number here. Let's say it was 0.0121. So it would be associated to my Z number. This is equal to the Z number, the area of the Z number 2.12. I gave you the formula earlier. We're gonna calculate the Z value. We're gonna round final answer, we're gonna round it to 2 decimal places, and then from there we're gonna look at the chart. Whatever numbers inside at that junction, that is the probability of that event. So let me give you an example here. What is the area of that number corresponds to? Remember, with this thing, it always it relates to all the area to the left of it. Kind of like one of those test scores, the standardized test scores, the quartiles. So here's your score. You're bigger than this many percent of the people. So since we have a 1.15, it's negative. Go to the chart that has the negative values on it. Go down the first digit. So we're going to go down to negative 1.1. To negative 1.1 is right down here. And then the second digit is 5. So we go to 0.05. So this column, this row, it equals to 0.1251. This equals to 0.1251. That's this area of that curve right there. So the probability of getting a number negative 1.15 is 1.1251. Okay, now what about this one? If I had a value of 2.03, what would be that area? What would be that probability? So we have to go to the positive chart. We look at on the left column, go to 2.0, and then go to column 3. So 2.0 is right here, 2.0. And there's 0, 0, 0, 1, 0, 2, 0, 3. That is the second digit. So it's 0.9788. Let's put together all this stuff same. What do these numbers represent? What do the z-scores represent? If you noticed, here's the mean. The mean is 0. That means anything to the left of the mean has to be what? Has to be negative. Sure enough, this one here is to the left, so it's negative 1.15. The one to the right of it is positive since it's to the right of it. What what the Z numbers represent to is how far is your number you're looking for away from the mean? It's looking for a ratio, a proportion. I'm just not showing you how to use the chart. What is the probability of getting a Z value greater than 1.03? You have the chart, you have everything you need in front of you. There's no reason you should be looking around unless you're finished. So what did you get? Nope. Think about what it says. Yes. Think about what it says. What is the value in the chart telling you? What I'm looking for, here's the mean, it's 0. I'm looking for a value that's 1.03. Greater than, I'm looking for this area here, aren't I? What does the number in the chart define for us? Look at the picture. What side of the number is it looking at? Looking to the left of it. So in order to find what's to the right of it, the whole thing has to equal 1. I know this area here is 0.8485. How do I find this area? 1 minus 0.8485. That's how much another example. So very important. It tells us whatever that value is to the left of it. These are what we call one-tailed tests. It only happens at one site. What is the probability of getting a Z value less than negative 2.11? So if we look at our picture, negative is to the left of the mean. So negative 2.11. I want less than, so I'm looking to the left of it. So what area is that? Point 0.0174. Because you go to, on the negative side, go to 2.1, go to 1.0174. Again, you see why these are called one-tail test, because they're only happening on one side. What is the probability of getting a z-score greater than negative 1.35 and less than 2.11? It always helps if you draw a picture too. You should always start off by drawing a picture, since we're dealing with bell curves here. Here's the mean. It equals 0. Now, what part of this graph am I looking for? What's that? The middle part. I'm looking for this area here. How do I find it? With what we talked about so far, how do you think I'm going to find this solution?
That's the.
Very good. Yes, that's exactly right. Both of y'all are right. Because remember, this 2.11 is everything to the left of it. And this one gives me to the left of it. So if I subtract those, so if I subtract the 2.11 minus the negative 1.35 z-scores. So the 2.11 is 0.9826. And I subtract the minus 135, 0.0885. 135, 3, 4, 5, 0.885. It's 0.8941. One more. And then we'll look at the formulas for it all. What do I do here? Go down. 8.3, yep. So we take that number, 1 minus 0.8438, 2651. Okay, you guys should see, the whole thing is you shouldn't just be copying. You should be doing this first and then using mine to check your answers. If you're just copying, then you're doing nothing. All right, let's look at some of these here. Example 3 in notes. Bone density. It says, a bone mineral density test can be helpful in identifying the presence or susceptibility to osteoporosis, a disease that causes bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as z-scores. The population of z-scores is normally distributed with a mean of 0 and standard deviation of 1. Find a randomly selected adult undergoes a bone density test. Find the probability that the person has a bone density test score less than 1.7. So which side am I shading, left or right? Left, because it says less than. So what's the answer? Very good. Okay, here's another bone density. Using the same bone density test, find the probability that a randomly selected person has a result above negative 1.00. We want above. So which side do we shade? The right side. That's what we're looking for. So what does the chart tell us? What remember, it always tells us to the left of the number. What number is it? Yeah, so this is 0.1587 from your chart. How do we find the other part? So this area is going to be 3148. Pretty easy. Okay. Example 5 is between two numbers. Between negative 1.00 and negative 2.50. Finished? We want between those, so we want that number there. So how do we find it? Yeah, so the probability, the percent of negative 1.0 is what? 0.1587. That's the 0.1. And we subtract from it. What's the area of 0.250? So yeah, this is going to be 0.0062. Because that's the one we don't want. Get rid of that. Yep. Those are pretty easy. Yes.
The part above the negative 2.50.
This,
Yeah,
this is the part we're looking for.
yeah, so what about the part on the other end?
Over here?
No. On
Over here?
Yeah, those lines, those are not over the.
Well, no. This area here was that.
Right.
That's this area.
Oh,
Because the number here was everything to the left. We want to get rid of this. That's why I subtracted. Good question. Finding z-scores from known areas. Okay, so an example here. Okay, now what do you think this is talking about? Finding z-scores from known areas. We're working backwards now. I'm going to give you the number inside the chart. You tell me what z-score corresponds to it. Because the reason that is because once we show you the formula that we'll be using to do the z-scores, we can now find exactly what value of X we're doing or what the mean is or anything like that once we have all the rest of the data. So for example, if I said the z-score, if I said the area was 0.0934. What is the z-score? No. Okay. Remember, it's either gonna be positive or negative, right? Think about what they mean. If it's negative, what side of the mean is it on? On the left side of the mean. And the mean is how many percent? 50% or 0.5000. So anything to the left has to be less than 0.500. Anything to the right has to be from 0.5001 all the way to 0.9999. So this number here is pretty small. So what side of the mean is it on? It's on the left side. So since it's on the left side, we have to look at the negative chart. So now we look for 0.0934. 0.0934, which is, yeah, negative 1.32. Not that hard.
I think I just said it's a positive side, but I know.
Yeah, right, it does. Let's look for an example. Oh, there should be something else in here. These notes. If your X that you're looking for is at negative 0.5, that value is 0.0000. Remember, that should be in the middle. If it's negative 0.45, it's going to be that. So these values, you see that if these are, because this number, negative 3.4, it goes all the way to negative 3.49. What happens from 3.49 to 5.0? That's what this is all about. Same thing on the other side. This chart goes down to 3.49. What happens beyond that? That's where you jump into these values. There's bone density. Find the bone density scores corresponding to one more. Yes, it is. Find the bone density score that separates the bottom, the probability of the 95 percentile. So if we were to draw a picture of this one, where would the 95th percentile be? On the very far right, yeah, but this is the mean, this is 0. This is 0.95 or 95th percentile. So what we're looking for here is what number? 0.95. So what number is that going to be? 0.95. What's that again? But what's z-score? If you look at the z-score, 0.95 falls between these two. Yeah, so we go 1.64 and 1.65. It's in the middle of it, so we take the average of those two. So this one is 1.64 plus 1.65. Add those together, divide by 2, we get 1.645. If it's exactly in the middle of two numbers, then you take the average of those two. All right, it'll be the same examples those coming up. So we're done with that section. The next section we'll do real world applications. That's all.